So thank you for that introduction. First, I want to say thank you to the organizers of this conference for the honor of the opportunity to stand up and speak to you all tonight. I'm Melissa, and I'm an undergraduate student at the University of Alberta, and today I'm going to be speaking about why sex doesn't matter, or to be more precise, the capillary blood volume response to exercise in men and women. So why did we want to study this? This formula shows the relationship between oxygen diffusing capacity, oxygen consumption, and then gas exchange, as represented by the alveolar arterial oxygen difference, or AA difference. When we rearrange the formula, we see that for any increase in oxygen consumption, there needs to be a subsequent increase in oxygen diffusing capacity for our gas exchange to be maintained. If that doesn't happen, what we would see is a widening of this AA difference, which could lead an individual to experiencing exercise-induced arterial hypoxemia. Two of the main determinants for oxygen diffusing capacity are alveolar volume and pulmonary capillary blood volume. With exercise, we recruit and distend capillaries so that we have a greater overall pulmonary capillary blood volume and a greater surface area for gas exchange. But in height and age-matched men and women, men tend to have much larger lungs. So we hypothesize that women may have a lower available pulmonary capillary blood volume. We're not the first group to study pulmonary gas exchange in men and women. This is from a review article by Hopkins and Harms, and it essentially shows the relationship between AA difference at peak exercise and VO2 max. And what we see is that women have a greater gas exchange impairment in comparison to men overall, and that this is heightened in our fittest individuals. So we thought that it may be that women are at this greater risk of gas exchange impairment as a result of lower oxygen diffusing capacity in comparison to men, and that may be because they have a lower pulmonary capillary blood volume. Some have hypothesized that there may be a limit to how much pulmonary capillaries you can recruit during exercise, and so we may see this as a plateau response. So the purpose of this study was to compare the capillary blood volume response in age and fitness matched men and women, and then compare the pulmonary diffusing capacity in these two groups. We predicted that because of their smaller lung size, women would recruit fewer pulmonary capillaries during exercise and then see a plateau in that response, and that we would likewise see, as a result of this, a lower pulmonary diffusing capacity when compared to men. This is a figure that nicely illustrates how gas exchange happens between the alveoli and the arteries. We used DLCO as a measure for oxygen diffusing capacity. Broughton and Forster conceptualized DLCO as a series of resistances where DLCO is composed of the diffusing membrane capacity, the capillary blood volume, and then also theta, which is the binding affinity for hemoglobin. With this formula and a multiple FiO2 method, we can estimate theta and then calculate our diffusing membrane capacity and capillary blood volume. So when we plot the relationship between these three different points, these three different FiO2s, we could calculate our capillary blood volume and our diffusing membrane capacity, where our capillary blood volume is the slope of the line, and our diffusing membrane capacity would be the y-intercept if we were to extend this line here. Our study was broken into two main parts. First, we would bring our subjects in and test their hemoglobin concentration and perform a resting pulmonary function test, including resting measures of DLCO, capillary blood volume, and diffusing membrane capacity. And then we did a VO2 max test with our subjects on a cycle ergometer. We brought them back for 3 subsequent test days, where we tested their hemoglobin concentration each day, and then asked them to exercise at 2 out of 6 possible workloads, ranging from 30 to 90% of their max exercise capacity. For every exercise workload that they performed, we brought them to steady state of exercise and then performed our 3 FiO2 measurements. We randomized our FiO2s and our workloads between test days, and prior to every DLCO maneuver, our subject was pre-breathed with that FiO2 for 5 breaths. For this study, we recruited 32 participants, including 16 males and 16 females. We height matched our individuals, and then also matched them according to percent of their predicted VO2 max. What's important to note in our subjects is that they all had good pulmonary function, and that with our females, we also specifically tested them during the luteal phase of their menstrual cycle. And what we did is we screened for participants that were specifically on hormonal birth control for this. What's most interesting here is that while we've height matched our individuals, there's a drastic difference in their total lung capacity or lung size, despite the fact that we height matched these individuals. When we look at our results, we see that our diffusing capacity, we see a similar kind of response in our males and our females. The males have an elevated response, or elevated values in relation to our females at every stage of exercise, but we see a general increase in diffusing capacity with exercise intensity in both groups. Now, with our two main determinants of diffusing capacity being our capillary blood volume and our diffusing membrane capacity, what was most interesting here is that our capillary blood volume did not show that plateau response as we had anticipated, but we see a continual increase up to our final workload. We took our workloads and we scaled them for every individual's percent of their VO2 max, and what we see is that quite cleanly, we see that same response between our two test groups, with males having a higher response or a higher value in relation to the females at every stage, and we likewise see that in relation in our other two variables. Now, you'll recall that our males have much larger lungs in comparison to our females, so we wanted to see what would happen if we tried to correct for the difference in alveolar volume. And what we see is that while we still have that effect of exercise intensity on diffusing capacity, our lines are now lying almost on top of each other, saying that the effect of sex has been removed. And we likewise see the same response in our capillary blood volume and our diffusing membrane capacity. Now, you'll recall from an earlier slide that it seemed that our fitter females were at a higher risk for gas exchange. So then we partitioned out our 7 fittest females and our 7 fittest males, and we compared them. And what we see here is that our females certainly don't have a lower diffusing capacity or a lower capillary blood volume. If anything, they may actually have a little bit of a better response in comparison to the men, which is quite interesting to see. So our overall finding is that on average, females have a lower diffusing capacity, capillary blood volume, and diffusing membrane capacity with incremental exercise, but when we control for alveolar volume, the responses are almost identical. So what this says to us is that while any differences that we might be seeing are as a result of lung size and not intrinsic differences in the pulmonary vasculature. Before I end, I just want to acknowledge all the collaborators and the funding sources on this study, and thank you for your attention.
Good time for questions, and Ben Levine arises again.
Just a comment and not a question. We've recently seen interesting stuff. We have pulmonary catheters in people, and they're at rest, and then they begin to exercise. And one thing that is immediately apparent is that their pulmonary artery pressure rises dramatically as they begin to exercise. So that picture that you had with the lung sort of, you know, the blood at the bottom of the lung resting, and then diffusing, and then the blood sort of going up and filling the total alveolar capacity, I think is sort of what our idea was. I'm just adding another observation that would sort of support what you were showing.
Thank you. It's definitely very interesting.
May I just ask, did you correct for hemoglobin differences?
Yes, we did. So we measured our hemoglobin concentration every day that we brought our subjects in, and then we used this middle formula here to adjust for the hemoglobin concentration with all of our measurements.
I'm not looking else. Thank you for that. Very difficult measurements. These are single breath deals.
Yes.
Yeah. You plot a lot of your plots at the end, and I can see what you're going through, trying to figure out how to standardize this. Different lung volumes, different absolute VO2s at a given percent. But the usual, traditional way to plot capillary volume is you proportional to the absolute VO2 rather than percent of mass. So I think if you want to know for a given blood flow through the lung, whether they're recruiting the capillaries similarly, I think that should be your plot.
So rather short our results across individuals' absolute VO2 rather than the percent of prediction.
To make it, in other words, as a surrogate for pulmonary blood flow. That still doesn't, get around the problem of different lung volumes.
Yes.
Things like that. That's it.
Thank you.
Thank you very